Hello everyone, welcome back to Labtube. In this video I'm going to discuss question 3 from chapter section 16.2, which asks to evaluate the line integral x y to the power 4 ds, where c is the right half of the circle x squared plus y squared equal to 16. So before I start, I just quickly recall how we evaluate a line integral for a function. So if a curve, the curve C is given by RT, T going from A to B, to evaluate the line integral f ds, we have to do 3 steps. First, go from A to B. We are changing everything to the variable t. So I go from A to B. F is going to have x, y, sometimes z. So what I need this time to put for that is just variables the values of RT, which are functions of t. That's the second step. Third step, I have to write down the integral element in terms of my parameterization, which is given by the length of r prime times dt. Those are the 3 steps. If you do those steps, you will get a regular integral, which by now you have to be able to evaluate such integrals because it's just regular integral with one variable. You do fundamental theorem of calculus and so on. Okay, let's do this question. For this question, C is the right half of the circle x squared plus y squared equals to 16. What kind of circle is that? It is a circle of radius 4 and its center is 0, 0. So it is a circle at centered at origin and the radius is 4. But we don't want to have the whole circle. It says just take the right half of it. So it goes from here to here. So if you're doing a line integral for function, you don't need to have the direction. Basically, you just find a parameterization for this. It doesn't matter which order, which direction, you just find a parameterization. And we all know that the right parameterization would be the parameterization coming from the polar coordinate. In this case, r is equal to 4, r cosine theta for x, r sine theta for y. And that's it. But to get right half circle, the angle, you look here. It is, if you see this way, it is negative pi over 2. It starts from negative pi over 2, goes up to 0, up to pi over 2. So now I have my parameterization and boundaries for my variable. Then I can go ahead and just plug in everything there. X, y, 4 ds. I'm going to apply all the steps I explained before. Write your integral in t, meaning that change boundaries of your parameter going from negative pi over 2 to pi over 2. Plug in your parameterization in your function. What does it mean? It means that plug in 4 cosine theta for x, 4 sine theta for y. And then you get 4 cosine theta times 4 sine theta to the power 4. That's the second step. The third step is find r prime and then its length. So r prime, let me do it quickly here. R prime t is going to be minus 4 sine t for cosine. Oh, I have to do everything in theta now. That's theta. So now the length of this guy is negative 4 sine theta squared plus 4 cosine theta squared d theta. Everything is written in your new variable or your parameter, and it is just a regular integral. So let me just simplify this, and then you will see how it goes. Here I have 4 squared sine squared, 4 squared cosine squared. I can factor out 4 squared, and I get 4 squared times sine squared plus cosine squared, which is 4 squared. Square root of that is 4. So I have 4 for this part. I have 4 here, 4 to the power 4 there. So I can put 1 4, 4 fours, 5 fours, 6 fours, 4 to the power 6. Oh, that's just constant. Then cosine theta sine to the power 4 theta. Let me erase this part. Now I have to evaluate this, but the good thing is that I have sine to the power 4, and derivative of sine is cosine. It is out there, so I can use substitution. Set u to be sine theta, and then the u is going to be cosine theta. That means I have du here. This is u to the power 6. And for boundaries, if if theta is negative pi over 2, then u is going to be sine of negative pi over 2. Look at your trigonometric table. It is negative 1. And if theta is pi over 2, then u is sine of pi over 2, which is 1. So then my boundaries, new boundaries are these guys. Why do I have 6 there? It is 4. It's just 4. Sine 4 is good. It is equal to u2. Then find antiderivative. Use fundamental theorem calculus. So it is 1 over 4 plus 1 u to the power 4 plus 1. Go from negative 1 to 1. And this is 4 to the power 6 over 5. Plug in 1 here. It is 1 to the power 5, which is 1, minus negative 1 to the power 1, which is negative 1, and you multiply. You get the result is 2 times 4 to the power 6 over 5. And that's the answer. Quick wrap up. You have to apply this formula when you're trying to evaluate line integral for function. First, we found the parameterization for our curve. In this case, it was just circle, half circle. We found the right boundaries for that. Then I did apply all these 3 steps. Change boundaries, change variable of your function, write down your line integral in terms of your parameter. And then we got a regular integral, evaluated that integral. Thank you for watching this.